Up to this point, we have done a lot with equations. We've learned how to graph, we've learned how to determine if something is a solution or not, we've learned how to find the slope, the y-intercept. Now in this lesson, we are going to learn how to solve systems of equations. So the question is, what is a system of equations? Well, a system of equations is simply a set of equations that you look at the same time. So it could be 2 equations, it could be 3 equations, but you're looking at all of them at the same time. Now, as far as systems are concerned, a solution to the system would be an ordered pair or a set of ordered pairs that satisfies both equations at the same time. So for example, if you're given these 2 equations, y equals negative 3x plus 8 and y equals 2x minus 2, the question is, would the ordered pair 0, 8 be a solution? Well, to determine this, what I do is I see, would 0, 8 be a solution to both equations? So it cannot just be a solution to one, but it has to be to both. And you've learned in a previous lesson how to determine if it's a solution for one equation by simply plugging these numbers in to the equation. So the first number in the ordered pair is your x value, second number is your y value. So looking at the first equation, I could plug a 0 here in for x, and then I could plug an 8 over here in for y. So when I do that, I have 8 equals negative 3 times 0 plus 8. Negative 3 times 0 is just 0. So you have 8 equals 0 plus 8, which would be 8 equals 8. So therefore, it would be a solution to that first equation. Now for the second equation, I plug an 8 in for y, and a 0 in for x again, to get 8 equals 2 times 0 minus 2. So we have 8 equals 0 minus 2, so 8 would be negative 2. So notice it would be a solution for the first equation, but not for the second one. So therefore, it would not be a solution to the system. And for it to be a solution, we need it to be true for both. So let's look at another example. Using the same equations, let's try to see if 2, 2 would be a solution to the system. So remember, this first number is your x value, second one is y. And so in place of x, I'm going to put a 2. And in place of a y, I'm going to put in the other 2. So here we have 2 equals negative 3 times 2 plus 8. So 2 equals negative 6 plus 8, which would equal 2. So 2 equals 2. That would be a solution for the first equation. Now the second equation, same thing. Plug a 2 in for y, and then the other 2 plug in for x. So what I have is going to be 2 equals 2 times 2 minus 2. 2 times 2 is 4, so we have 4 minus 2, which would be 2. So therefore, we have a true statement, which would mean that it's a solution for that second equation. So 2, 2 is a solution for the first equation, and it's also a solution to the second equation. Therefore, 2, 2 would be a solution for the system. And that is how you determine if something is a solution or not. Now, graphically, what does that mean? Well, a solution is an intersection of both lines. So if there's one intersection, then there'd be one solution. So, for example, here we have 2 lines that intersect right here at one point. So therefore, graphically speaking, because there's one intersection, there's one solution to that system of equations. And by the way, each equation is a line, right? So those equations we're dealing with would be represented by lines. And so what we're finding is where they intersect. And so if there are no intersections, meaning the lines are parallel, then there would be no solution. And then the last example you might have would be coinciding lines, meaning here's a line and then there's another line on top of it. That would be coinciding lines. And notice they intersect at every point on the line, and it's going to keep going forever and ever. So therefore, there would be an infinite number of solutions. So if you're given a system of equations, what you could do is you could graph both equations on a Cartesian plane and see where do they intersect. Wherever they intersect, that would be the solution. However, it's kind of difficult to just guess or guesstimate where they intersect, because it could be some fraction, right? It could be intersecting at 2.36 for x, and then y could be 4.89 or some decimal like that. So therefore, you do not want to have to estimate where they intersect. But what we can do is we can algebraically solve to figure out where do these two equations, where do these two lines intersect. So when you solve a system of equations, we can do two things to solve. We can add or subtract. So add or subtract two equations together. And the other thing we can do is we can multiply an equation by something. So if you have an example, let's say you had x plus y equals 4 and negative 2x minus y equals 3. So here, if I try to add these equations, notice what happens. This y plus a negative y would cancel, leaving me with 0. X plus negative 2x would give you a negative x. And then 4 plus 3 gives me 7. So when I just add these two equations together, notice that this variable, the y's, will cancel, which is what my end goal is. I want to get something to cancel so that I'm left with one variable where I can solve for that variable, and then I can use that to find the other one. So here we only have one variable left, negative x equals 7. We want to figure out what is positive x equal to. So to get rid of the negative, I can divide both sides by negative, or negative 1, same thing. And so when I divide both sides by negative 1, this becomes a positive x. 7 divided by negative 1 gives you a negative 7. So we have solved for x, and the question is, though, what is y going to be? Because there's two variables, right? So to solve for y, what I do is I can pick either equation, does not matter which one, and I substitute this negative 7 in for x. So looking at that first equation right here, if I plug in a negative 7 in for x, instead of x plus y, I'd have negative 7 plus y equals 4. And then to solve for y, I simply add 7 to both sides. So I get y equals 4 plus 7, which would be 11. So my solution would be x is negative 7, y is 11, which can be written as an ordered pair. So what we've done is we have found that if we were to graph these equations, then they would intersect right up here at negative 7, 11. So instead of having to draw it out and then look at the graph and figure out where they intersect, we can just solve algebraically instead. Here's another example. This one is like a level 2 difficulty, because here, when I try to add, nothing will cancel right away. So when I try to add, say x plus 4x, I would get 5x. That does not cancel. Negative 2y plus 3y, I'm still left with 1y. That does not cancel. Now it's not wrong to add like that, but it's not helpful. So what I need to do is figure out how can I get this to cancel when I add them or subtract them together. So let's say this first equation, let's say this first variable, say it was a 4x. If it were 4x here, well then when I subtract, I could subtract the two equations. 4x minus 4x would cancel, and I'd be left with just the y's. So what I would like is there to be a 4 here. Well, how do I get a 4 there? What I can do is I can multiply everything by a 4 in that first equation. So here, that first equation, multiply everything times 4. So when I do that, I'm now going to have 4 times x. Negative 2 times 4 gives you negative 8y. 6 times 4 gives me a 24. And I did that once again because I can either add or subtract the equations. And when I add or subtract them, notice 4x minus 4x would cancel. So that is my end goal. I want these to cancel, so I'm left with one variable where it's easier to solve. The only thing is, if you're subtracting, be careful when you have the negatives in here, because you have negative 8 minus a 3. Negative 8y minus 3y would give you a negative 11y. And then 24 minus 2 would be 22. So then to solve for y, I need to get rid of the negative 11. And this is negative 11 times y. So to get rid of the negative 11, I divide both sides by negative 11. And when I do that, I now have positive y equals 22 divided by negative 11, which would be negative 2. So I'm halfway done. I've solved for y. Now I need to figure out what is x. Now it does not matter which equation I use, but let's use this first one right here. So instead of x minus 2y equals 6, what I have is x minus 2 times negative 2 equals 6. So I just replace this y with a negative 2. So negative 2 times negative 2 is a 4. And then what plus 4 equals 6? Well, that's going to be 2. So now we've solved. X is 2, y is negative 2. And we can write that as an ordered pair. And by the way, it's always good to check to see if you got the correct answer. So let's check this one to make sure. So we can plug in a 2 and a negative 2 in for x and for y. So instead of x minus, we have 2 minus. And instead of 2 times y, we have 2 times negative 2. So then 2 minus 2 times a negative 2 would be a 2 plus 4. Negative 2 times a negative 2 is a positive 4. And then 2 plus 4 equals 6. So therefore, that works for this first equation. This would be a true statement. And then for the second equation, instead of 4 times x, we have 4 times 2. And instead of 3 times y, we have 3 times negative 2. So we can solve this. 4 times 2 is 8. 3 times negative 2 is negative 6. So 8 minus 6 would give me 2. So this would also be a true statement, meaning that we have the correct answer. It has given us the correct solution for both. And then, graphically, what we have found is if we were to graph those two equations right here, then they would intersect at 2, negative 2. So that's what we've done. We found where do they intersect. But instead of graphing it to determine, we have used algebra to figure that out. Here's another example, and this one is definitely the most difficult, and I consider this a level 3 difficulty. Here we have two equations. Now notice here, we try to add or subtract, nothing will cancel. If we try to add right away, we'd have 3x plus 2x, which would be 5x. That does not cancel. We'd have 4y plus 3y to get 7y. That does not cancel. And same thing with subtracting. We'd get 1x or 1y. So nothing cancels by addition or subtraction. So what I need to do is I need to multiply one of the equations by something so that they will cancel. However, if we look at the x's, to get from a 2x to a 3x, there's no whole number to multiply the 2 by to get to 3. Right? If we multiply this bottom equation by 2, we'd have 4x, not 3x. So that doesn't work for the x's. For the y's, to get from a 3 to a 4, there's nothing to multiply by to get from 3 to a 4. But what I can do is, in this case, multiply both equations by something. So if you look at the x's, for example, if you multiply this top equation, so the 3x plus 4y equals 6, multiply that let's say by the other number. So if we're trying to get the x's to cancel, if we multiply the 3x by a 2, that would give me a 6x for that first equation. So this would become a 6x, this would become an 8y, this would become a 12. And then if I multiply this bottom equation by this other number, the 3, So multiply by 3, we'd get, once again, 3 times 2 to get 6x. We'd have 9y, and we'd have 15. Notice by multiplying each equation by the opposite number, by the opposite coefficient, what we've done is we now have a 6x and a 6x. We could have done the same thing with the y's, where multiply the top equation, since you're dealing with 4y and 3y, multiply top equation by the 3 for down here, and then multiply the bottom equation by the 4 because of the 4y for the top. So we just kind of flip-flopped. And now let's finish this one off, where now we have multiplying top by 2 and the bottom by 3. We now have 6x plus 8y equals 12, and then 6x plus 9y equals 15. So I multiplied by the 2 and the 3 because now, notice when I subtract 6x minus 6x, these will cancel. And that is why I did that. Because those will cancel. I'm left now with 8y minus 9y, which becomes a negative 1y. And then 12 minus 15 gives me a negative 3. Notice we have just one variable, so we can solve this right away. So negative y equals negative 3. Divide both sides by negative 1. We're going to get positive y equals a positive 3. So we're halfway done. We found y. Question is, what is x? Well, I can pick either equation, and actually I can pick any of these 4 equations. They're all the same thing. They'll all give you the same answer. But if we just pick the first one up here, we plug a 3 in for y. We now have 3x plus 4 times 3 equals 6. 4 times 3 is 12. And then to solve this, just subtract 12 from both sides. And we get 3x equals negative 6. And then divide both sides by 3. We get x equals negative 2. So our solution would be x is negative 2, y is equal to 3. And it's always good to check our solution to make sure that it's correct. So by checking, we plug in negative 2 and 3 in for x and y for both equations. So the first equation, 3x plus 4y equals 6, plug a negative 2 in for x, plug a 3 in for y, we get negative 6 plus 12 equals 6. So therefore 6 would equal 6. That is a true statement. So the first equation is good. Second equation, do the same thing, plug a negative 2 in for x. So instead of 2 times x, we have 2 times negative 2. And instead of 3 times y, we have 3 times 3. We get negative 4 plus 9 equals 5. So therefore 5 equals 5. That is a true statement, which means because both are solutions, they're solutions of both equations, we therefore have the correct answer. And then once again, graphically, what we have found is if we were to graph those equations, our intersection would be right here at negative 2, 3. Here's another example where our answer is going to have fractions. And I'm showing you this one because many times students will not know what to do with fractions, even though everything is exactly the same. But I'm going to show you one here just to make sure that everyone understands. So for this one, we have this system of equations. And notice if we subtract right away, x minus x, this will cancel. So I can subtract right away, and those will cancel. And then we have y minus negative 3y becomes a positive 4y. 4 minus 3 becomes a 1. So we're down to one variable, which is what we wanted. Then divide both sides by 4. We have y equals 1/4. So here we have a fraction. So to get this first one, that's not too bad. But then the issue comes in when you plug back in. Some students make mistakes, so be careful. We can use either equation, and let's use the first one just for simplicity. And so when we plug that in, instead of x plus y, we have x plus 1/4. And then solve for x, we subtract 1/4 from both sides. And we have x equals 4 minus 1/4, which becomes 3 3/4. And our solution then would be 3 3/4. Y would be 1/4. And I show the steps here for subtracting for those who cannot do that in your head. But this would be your solution. And then always check your answers. So when you check, I'm going to kind of fly through this, but you plug this 3 3/4 in for x, plug this in for y, and 3 3/4, when you plug it back in, it might be helpful to keep it as a improper fraction. Either way, it doesn't matter, but 15/4 is the same thing as 3 3/4. So when you take the first equation, you get 16/4, which would equal 4, so that one works. And then the second equation, x minus 3y equals 3. X is 3 3/4, or 15/4, minus 3 times y, so 3 times 1/4. So 3 times 1/4 is 3/4. You subtract, you get 12/4. 12 over 4 would equal 3. So it works for both equations, therefore we have found the correct solution. And once again, graphically, here's what we found. We found that when they intersect, they meet right here at this black point, 3.75, comma, 0.25. Now there's two special scenarios I need to point out to you that you might run into. So this example, notice when you solve this one, we can start by adding right away, because when you add, your x's will cancel. X plus a negative x, these will cancel. So x plus negative x leaves you with a 0, and then y plus negative y would also cancel. So you have another 0, and then 3 plus 5 gives you 8. So what we have is 0 equals 8. Notice there's no variables left over. It's a very unique situation, and what we have found is that because this is a false statement, we call this inconsistent, meaning that there's no solution. And if you were to graph this, your two graphs would look like this, where we have two lines that are parallel. And remember that if two lines are parallel, there's no intersection, so therefore no solution. The solution is where they intersect. So when you see something like this, where it's a false statement, 0 equals 8, you can conclude automatically that it would have no solutions. And the term we give to that would be this term right here called inconsistent. The other kind of example is, let's say you had these two equations and you try to solve this one by adding. When you add, notice that x's will cancel again. So you have 0 over here. And then y plus a negative y, this would cancel. I'm left with another 0. And then 3 plus negative 3 would also equal 0. So what we have is a statement where 0 equals 0. If you run into any statement like this, where now there's no variables left over, and you have a true statement, what this means is that we have an infinite number of solutions, which we say, the term we give is consistent, and more specifically, we say that they are dependent. So when you see consistent and dependent, that means there's an infinite number of solutions. So what we have is actually two lines that are on top of each other. So here just shows up as one line, but that's because they're both on the same line. So because we have an infinite number of solutions, it's going to be two lines like this. And by the way, it doesn't have to be 0 equaling 0. It could be 4 equals 4. It could be 7 equals 7, as long as we have a true statement. So once again, to recap, inconsistent is when there's no solution. Consistent just means that there is a solution. So consistent could have one solution or infinite solutions. So this word here, the dependent, means that it's infinite. And then there's another term, all the other ones we've been dealing with, where there is a solution, we say that they're also consistent. And then if it's one solution, we say that they are independent. So independent means one solution, and then the dependent means infinite solutions. And that concludes our lesson for today, and we will see you next time.